Okay, so yes, we were discussing Ohm's law. So yes, what was Ohm's law? Ohm's law was yes, all physical quantities that should remain same. Like there should be no change in physical appearance. Oh God, sorry, no change in physical appearance. That physical appearance could be temperature, pressure, humidity, or many others. So what was exactly Ohm's law? That was saying there should be no change in physical quantity. So then the potential difference which will be flowing through the conductor should always be directly proportional to the conductor. How? If there's a potential difference which is directly proportional to what? Directly proportional to I, which is, oh sorry, potential difference which is directly proportional to I here is a current. So how we discuss that? If this is a material, if it's any material, okay, from here I, like current is flowing, I is here, current is flowing, and here what we have, here we found potential difference. So whenever current is flowing, that is, if we'll increase current, then potential difference will also increase. If we'll decrease, potential difference will also decrease. So what does this specifically mean? This mean potential difference is directly proportional to I, which is current. So we were done till the scalar quantity. What was the scalar quantity? First thing we know that we have an. Let me just erase this a little bit. So that was potential difference, which is directly proportional to what? To current. Okay, till this we were done. Then we know this is potential difference. Potential difference is a scalar quantity, whereas I is a current, which is also in a scalar. I'm sure you will be thinking it's not a scalar. Yes, that's a tensor quantity, but we cannot say it's a vector quantity. So we consider this as an scalar. So the product is also an scalar. And we also write this equation as delta V is directly proportional to the I, which is current, and resistance. Okay, so this was a scalar quantity, but what? There should be something which we can say potential, like that works as a potential difference. If you're finding potential difference, so we just say this as electric field, because electric field literally works like a potential difference. So EF is electric field, and we know that electric field is a vector quantity. Vector quantity, whereas potential difference is a scalar, and I here is a current, and current is also a scalar. No matter if it's a tensor, but in comparison of a scalar and vector, we consider this as an scalar. Then instead of potential difference, if we add electric field, the work will always same, and instead of a current, we insert charge density, which is denoted by J, and arrow on above tells that this is an a vector quantity. So this is also a vector quantity, vector vector quantity. And here we have resistance, which is also resistivity rho. This is also an scalar, not a scalar but the vector quantity. So we just get a product which is E, that's equal to what? That equal to J and dot P not rho, sorry. So this is an vector quantity, and this is an scalar quantity. And yes, a very most important thing that we also have ohmic and non-ohmic. So these all condition would be applicable until unless that the ohmic and non-ohmic condition are followed. So we have two types of conductors, ohmic and non-ohmic. Ohmic simply means which follows the Ohm's law. This means if the current directly proportional to potential difference, and non-ohmic which does not. So metal follows, whereas gases or semiconductor does not. Semi, and they have the graph, it's straight, that is curve. Okay, curve like straight.